All right, today we're doing locality-sensitive Today we're doing locality-sensitive hashing and approximate nearest neighbors. First, a trip down memory lane, as always. Our first lecture was about linear expectation, followed by some heavy hitters. Third lecture was linear probing and sort of taking those same tools and making them a little stronger. Lecture 4 was our first graph algorithm, where we did randomized minimum cut. We had another graph-based lecture when we did random graphs in a giant component, although really the conceptual emphasis was introducing the Chernoff bounds. The class after that, we did some approximation algorithms, in particular randomized rounding, linear programs. We did distinct elements, which we did a lot of analysis based on variance, and also introduced the median trick. And in last class, Thursday, I think, we did dimensionality reduction, which is really all about Gaussian random variables and all their nice properties, which leads to this kind of surprising result that insofar as we want to preserve distances between points, log n dimensions suffice. Okay. All right, so today also is sort of going to be about high dimensional stuff. And we're going to, in particular, study a very practical problem called nearest neighbors, although we'll have to do it approximately because we're working in high dimensions. And the technique we're going to be using is called locality-sensitive hashing. It is indeed hashing, but well, it's going to have some peculiar features. Usually when we do hashing, we want the keys to be spread out uniformly. We don't want collisions. Okay. But today we're going to do something a little bit different, and we're going to try to encourage collisions when points are nearby and stuff like that. And that'll actually lead to some better than nothing bounds. Okay. So it's kind of neat. All right, so nearest neighbor search, a very basic problem. We have endpoints in RD, so really you should think of D being very large. That's going to be our focus today. I don't know, maybe each of these represent images or tons of pixels or something like that. So you have endpoints, that's sort of like your database, and you get some query point, Q, and you want to return the closest point. Okay, simple enough. Extensions include, I don't know, give me the 5 nearest neighbors, so on and so forth. But we'll just focus on returning the nearest neighbor. So, okay, so maybe the most natural thing that comes to mind is to do Euclidean distance like we did last time, the L2 norm. I guess you could do any LP norm if you wanted. Some may be better suited for some applications than others. We'll probably only look at the L2 norm as far as norms go. But another type of distance we'll actually look at it first because it's a little bit easier technically, is we'll look at angles. So here maybe you have a bunch of points that are on a sphere, a high dimensional sphere. And so the angle between 2 points represents their distance. Okay, so if you want the nearest neighbor for that, you want the point with the smallest angle. All right, so as a warm-up, to build some intuition, or just make sure we're on the same page, let's look at nearest neighbor search in one dimension, just doing distance on the line. Okay. So you have some point set on the line and you want to be able to query for the nearest neighbor. How might you approach this problem? Yeah, we can sort and do binary search. Alternatively, you can build, a binary tree over it, which is implicitly the same thing, right? And if you're going here, you say, oh, get me the first point that's, give me the point that's, whatever, the biggest point less than it, and give me the biggest point that's greater than it. We get 2 points. We'll see which one's closer. We'll return that, right? Okay, fine. So that'll take like log n time. And if you want to do this in higher dimensions, there are analogous data structures like KD trees and quad trees and stuff like that. But you're basically going to pay some exponential dependence on the dimension. Okay, this can sometimes be improved a little bit, but besides the point. Okay. So this kind of old-fashioned binary search tree and generalizations is fine in 1 dimension, 2 dimensions, 3 dimensions, but not too much more than that. Okay, so our goal is to develop techniques with essentially no dependence on the dimension, sort of like what we achieved last time. That's what makes the problem hard. All right, so we'll start with angular approximate nearest neighbors and angular locality-sensitive hashing. So one thing to keep in mind is that we're really thinking about a really high-dimensional sphere and points on a high-dimensional sphere. For lack of imagination, this would be a 1-dimensional or 2-dimensional sphere, right? But what makes the problem more hard and complex and interesting is the fact that it's in high dimensions. So don't let that picture fool you too much. Okay, so you query some point on the surface, and then you want to find the nearest angle point. So is it that angle or is it that angle? I don't know. We'll compare the two, something like that. Of course, if it's just this, you could probably build a binary search around the outside, but again, in high dimensions, you can't. All right, so fine. So when we approach this, okay, maybe one takeaway that will come from this lecture is the following. So in general, hashing is always a good idea. Like hashing works really well in practice, okay? And maybe the first conceptual question is, if my goal is just somehow to use hashing to solve problems like this, how can I even break it down into such a form? So I think this first step is kind of conceptually important, although simple, which is that we are going to sort of break down the problem and frame it as follows. So my goal really, instead of trying to just get the nearest neighbor right away, is I'm going to fix some angle theta. Think of theta as the true closest angle. And at some level, I just want to get kind of approximately close. So we're going to come up with an approximation criteria. So when I'm querying a point Q, okay, so maybe here's Q, okay, and maybe theta, this prefigured theta, carves out roughly that amount of space, okay? So I have two choices. One is I can output some point that's, say, within a constant factor of theta. Here I chose 4 because apparently it was convenient. Or I can declare there's no point that's within theta. Okay. So in that example up there, I do have to output a point because there's definitely a point, at least one point within theta, in fact, and there may be several points within 4 theta in terms of the angle. Okay. But if theta was so small that there was no point in between, and then I'm allowed to output nothing. Okay. But there's some room for error, right? So if I outputted a point that's 1.5 theta away in terms of the angle, that doesn't necessarily tell me there's no point, with something at most theta or not. Okay, so I'm going to do this sort of approximation criteria, and I have some wiggle room. Okay, that's important. All right. Okay, so. Okay, I thought I would at least solicit ideas. I think what we'll end up doing is maybe unusual, so I don't know if this is guessable, but still I would maybe try to solicit ideas from you guys for this kind of problem. So imagine this is in really high dimensional space. Not sure if anything is guessable, but I'll let you guys try. Any ideas? Yeah.
Based on like how keyword you use, I feel like if we can somehow have a hashing algorithm where all the points within, like say, 4 theta of each other will have a collision, then the point producer will just hash the point Q and see if there is a collision with point Q, then we return that point. If there's no collision, we like declare there's no point near.
Okay, good. This gives me some teaching ideas. Okay, so all right, so we want to use hashing somehow, let's say. And so this is a reasonably good idea. It would be great if I could come up with a hash function so that points that are within theta of each other collide and points that are further than theta don't collide. So let's not worry too much about the high dimensional part and just look at this two-dimensional picture and see if we can develop some ideas. You're not allowed to use binary trees or something that would only work in low dimensions, but how, so say I have these points around the ring. What might be a good way to generate a hash function? You don't have to give me like a numerical formula because that would be kind of awkward, but maybe just draw a geometric picture. How can I try to sort of divvy up, in some sense, that pi so that points that are close together tend to be hashed together? Oh, okay, quadrants. I can try dividing, I can divide the space up by 4 or something, right? I have 4 buckets, and if they're in the same bucket, they're at least in the same quadrant. That's, I think, a good idea. Of course, you have some bad luck, right? So those 2 points, they're kind of close together, but they happen to be across the line of the quadrant. But, what's something we can do to help address this, at least on average? We can use multiple hash. Yes. But give me, oh. We could randomize the quadrant, right? Spin those 4 lines. So, okay, sometimes a line is going to split those 2, unfortunately. But the closer they are together, the odds of them being split, the lower it is, right? So there is some bias towards, the closer together, the odds of them not being split up. So maybe one generalization then, sort of using multiple hashes, and I mean, why should we do quadrants, or why should we do many lines, or why should we do little lines? I don't know. We can draw a bunch of random lines going through the middle. I'll kind of slice, that's not through the middle. Something like that, right? And kind of randomly slice it up and hope that things closer together aren't split up as much on average. Now, the flip side, why do you want many hashes? Because in some sense, if I only had one line, then I'm never splitting up the close points, which is good, or less and less, right? With fewer lines, I'll split them up less. The only downside is we would have to scan a longer list to find a nearest neighbor, right? So given my query point Q, I would just figure out kind of which side of the yellow line to go to, and then I would just go through that whole list and compare everyone. So that's the basic kind of one of the trade-offs we're fighting, that the more hash functions, the downside is I might split up points I don't want to split up, but on the other hand, the hash buckets are getting smaller, so when I scan, it's faster. Okay, and at some level, okay, it's a simple, nice idea. It's not really clear that this idea is strong enough to really win you anything and really get you a speed up compared to, I don't know, scanning everything the old-fashioned way. Okay, so that's very similar to what we're going to do, but we have to somehow make this idea work in high dimensions. Yeah, maybe I can ask. Even for a three-dimensional, yeah, or okay, so how would I generalize this idea to high dimensions? Of course, I wouldn't be able to draw it. Yeah, so yeah, I guess algorithmically, you know, So somewhere there's a center of a sphere, I guess. And if you pick a random point on a surface, I don't know if this is going to come out well, right? And you draw this like ray out to the sphere, and then you can kind of project. You can see if like points project onto it in a positive way or negative way. All right, whatever. Here's a different way to do it. Okay. What we're going to do is we're going to sample a random Gaussian, G, okay? And then I'm going to look at the inner product of, say, some point X and G. Okay. Sampling random Gaussian is functionally the same as sampling a point on the sphere, but we'll get to use some tricks from Gaussian random variables in a moment. So I'm going to take the inner product of G and X. So I'm going to multiply and sum up their coordinates and then look at the sign. Is it bigger than 0? Is it less than 0? So that would give me a 1 or a negative 1. That would be 1 bit of a hash code. Okay. So that's what we're going to analyze. And the claim here is that the probability that the signs of 2 points, when projected against a random Gaussian, are not equal is proportional to their angle over pi. Okay. So what does that say? The further apart they are in angle, the more likely their signs are different and they're in a different bucket. Okay. And it's also equals, so you have the other direction as well. The smaller the angle, the smaller the odds of disagreeing, the higher odds of agreeing. Okay. All right. Okay, so this proof is actually easier than you would suspect. It's easier than I suspected. All right. But where do we start? The first step would take advantage of a nice property of Gaussians. Well, okay. Well, do we agree that this proof would be easier if it was in 2 dimensions? Yeah, okay. So it would be nicer to do 2 dimensions, and as usual, we're queasy and uncomfortable with high dimensional things. Okay. Now, while originally X and Y might have been, on the surface of some high level sphere, right? We can always look at a plane on which X and Y both sit. So there is some perspective where they sort of both have X and Y coordinates and Z coordinates 0. Okay. So they do exist on a 2-dimensional subspace. And what's great about Gaussians is that they're rotationally invariant. So I can rotate the space, make it convenient for X and Y, and still have a Gaussian. Okay. So in fact, you can assume you're working in 2 dimensions, and you're only interested in really the first 2 coordinates, and the last d minus 2 coordinates are irrelevant. Okay. All right, so that's a nice math trick, thanks to Gaussians. Now, we know that the Gaussian basically is going to make some angle, right? And it can be any angle uniformly at random. It's completely symmetric, right? Okay, so, all right, so let's say I pick this angle here, something between them. Okay, so let me draw some lines. So we have this, and this part is the angle between X and Y. Okay. Oh, did I get this right? Okay, so this should be okay. So, all right, so if I draw, I hope it's okay. All right, so once I fix this Gaussian, right, everything that's sort of on one side of the dashed line is going to have a positive projection onto it, and everything on the other side is going to have a negative projection. Is that right? Okay, good. Okay, so let me do it differently. Okay, so let's first focus on x. Okay, so so if the Gaussian vector I pick is anywhere on this side of the green line, nope, got that backwards. Let me do it again. Okay, so let me draw something perpendicular to x. If the Gaussian is anywhere on this side of the green line, okay, then x will have a positive projection onto it. Good. And now let me draw a yellow one. Okay. If the Gaussian is anywhere on this side of the yellow line, then y will have a positive projection onto it. Okay. So for x and y to both have a positive projection onto this thing, we need to be in this region. Okay. And also, if we're in this region, they'll both have a negative projection. Okay. And for some, I don't know if I drew this very well. All right. This should be, oh no, okay, I get it now. Okay, so if you can kind of see it in this picture. I'm out of colors. Okay. This region where they get things wrong, on the other side of the green and yellow, this is the same as the angle xy if you work out the arithmetic. And up here would be 1 minus angle xy. Okay. All right, so I realize this looks kind of crazy. That's okay. All right. Okay, so that's the proof by picture. Any questions? Fine. Now here's the fun part then. Okay. All right, so fine. So we've created this function where roughly the odds of colliding is somehow proportional to the angle. Okay. So how might I turn this into a data structure? I guess you guys have already suggested this, so I'm just getting you guys to say it again. All right. So we're going to define a hash function where we have k coordinates. We'll figure out what k will be in a moment. Each coordinate is going to do one of these Gaussian projections. Okay. And the algorithm, as has already been suggested, is we'll take our input point P and we'll group everything by hash code. Okay. And to query a point Q, I'll just go to the list of all the points with the same hash code as the query point, I guess Y, not Q. Okay. All right, so fine. All right, so now, okay, so what we'll do. All right, so we want to analyze two things. We want to analyze, okay, if 2 points are pretty close by, where close is defined as angle theta, what are the odds that we get a collision like we want? We want close points to collide. And afterwards, we'll analyze, oh, what if they're far apart? What are the odds they collide? Okay. All right, so what do we know? The probability that h of x is equal to h of y is equal to, okay, what do we show? 1 minus the angle between them over pi. And we have k coordinates, right? Okay, fine. And, okay, so this is roughly, for small theta, e to the minus the angle between them over pi times k. Okay, fine. Let's leave that there. And on the other hand, oh, well, let me do one more. We know this thing is at most theta. Okay, so we get at least e to the minus theta. And on the other hand, okay, if I want to look at 2 points that are far apart, the initial calculation is the same. The angle between them times k over pi, okay, which is e to the minus, I guess, 2 theta. Okay, so, all right, so I want to somehow show this on the same screen. So on one hand, we showed when the angle is at most theta, we showed that this was at most, roughly at least, e to the negative theta k over pi. So, okay, so we have some small gap here. This is e to the negative 2 theta, this is e to the theta. So roughly the odds are squaring, it would seem. Okay. So now what we're going to try doing is we're going to set k to be pi log n over 2 theta. Okay. In that case, this would become minus k. The k should disappear if we substitute in k. E to the minus log n. Okay. So we'll get 1 over n. I should have wrote natural log, but oh well. Whereas here, we would get okay. So we'll do about log n copies. And now we have this gap. I have a 1 over square root n chance of winning on a good one, and also a 1 over n chance of losing on a bad one. Okay. Doesn't seem like much, but there's some separation. Okay, so, all right, so when I'm thinking about the algorithm then, if there is a near neighbor, something within distance theta, then we have a 1 over square root n chance of getting it. better than 1 over n, I guess. And on the other hand, you're going to, when you scan the bucket, you may be scanning points that are far away, and that's wasting your time, right? So the goal is to try to minimize those. We're only expecting to collide with at most one point that doesn't count as a near neighbor, because it was 1 over n in linear of expectation. N times 1 over n gives us 1. Okay. All right. Okay, so, all right, good. So now you know kind of how to succeed with probability 1 over square root n in some sense. It'll roughly take constant time, because or maybe log n time, you compute the hash, and there's log n bits. And then you go to the bucket, and maybe you look at one point on average that's useless, and you succeed with probability 1 over square root n. Okay, so it's very fast, but of course we want to succeed with higher probability. How can I ramp this up? Yeah, how many times to get constant? Probability of success. Or high probability, anything's fine. How many times should I? Don't be shy. Square root n, right? So in general, whatever your probability of success was 1 minus 1 over z for whatever z, and you repeat it z times, right? This is roughly e to the negative z over z, and you get e to the minus 1. So that just gets you to a constant, and you do it log n times more than that, you get yourself a high probability thing. So if we repeat it square root n times, or square root n log n, we will find a near neighbor if it exists with high probability. Okay? So if I repeat square root n log n times, what's my roughly my running time? I won't emphasize logs, I'll hide it under the tilde. But we repeat square root n times, and roughly each time, okay, I might look at one useless point until I find my nearest neighbor. Okay? So up to logarithmic factors, it's taking a square root n time to find a near neighbor. Okay? All right, so somehow with this hashing trick, we can do much better than scanning the entire point set. Okay. All right, any questions? We'll do Euclidean one next. We might finish early. Isn't that exciting? So I usually have like some coffee before coming to class, but then today before class, I couldn't remember if I'd already had coffee. So I didn't get another one. But it's starting to dawn on me that I probably didn't have that coffee earlier. Okay. Try to keep my energy high. All right, so that was the angular case. Now we'll move to maybe what would be more conventional, the Euclidean case in high dimensions, although it would be a little more technical to analyze. All right, so again, you have some points. This should be a high dimensional space, not a surface. So use your imagination. Given some query point, I want to return the closest point or some approximation of it. So again, I think an important, I didn't make this point earlier. I'll make it here instead. So a key conceptual step is somehow to set up the game in a way that's more amenable to hashing. That means two things: adding some approximation, because with hashing we're going to start making some errors. And two, do this thresholding idea again. Okay. So we're going to fix a radius r. That's sort of our definition of what it means to be a near neighbor. And I'll allow some slack sigma. Okay. So given some query point, I have two options. I can either return a point x that's within distance sigma times r. So maybe sigma is 2. So 2 times the desired radius. Or I can say there's no points within the desired radius. So again, I have some room for error. Okay. What I forgot to stress last time is how to use this parameterized version to actually help you solve an approximate nearest neighbor problem. So suppose your goal is to actually find maybe not the nearest neighbor, but something within a factor of 2 or a factor of 10%, some approximate nearest neighbor. And you know how to solve kind of these versions that are parameterized by some R, these single threshold versions. Okay. How can I take this and get like a more overall search for an approximate nearest neighbor? Oh, we can try different values of R. Now keep in mind, I want to make some kind of data structure or database or something like that. So I take all the points P and I build something to take in query points, right? So I don't want to kind of choose R's on the fly. I want to be more strategic. Let's say I want 2 approximate neighbors just to make the discussion easier, and then we can talk about more accurate. How can I take one threshold and build a more general data structure? If you want to do multiple values of R, for example, which values of R? Let's say you had a reasonable range on all the distances. You know that the minimum distance between any pair is, say, at least 1, and at most poly n or something. Okay, so you don't have to worry about things being too big or too small, something reasonable. Yeah. Okay, yeah, so maybe binary search on R. Okay, so it is a data structure, so I need to build something ahead of time. So I need to choose which R's. So what are some reasonable, yeah. Let's try all powers of 2. 1, 2, 4, 8, 16, and so forth. Now you're given some value Y, you don't know what the true R is. No big deal, right? So so now you've built it out for 1, 2, 4, 8, 16, whatever. Okay. And you have a point Y, what would you do? Where would you start? Yeah, you can try the middle value. And if you do find something that's within the range, try something smaller. If you don't find something, go bigger. Okay. And they should all succeed with high probability, so you can take a union bound kind of over all R's. It'll be only logarithmically many R's. Okay, so the threshold is enough to let you do binary search. Okay. Now I did powers of 2 because it's easier for us to think in terms of powers of 2. But what if I wanted a 1 plus epsilon approximation, where epsilon is say 0.1 or something, some smaller value? Not a power of 2, right? What would I do instead? Yeah. You just do powers of 1 plus epsilon, right? So you're going up like 10% each time or something. One thing you might worry about is how many powers of 1 plus epsilon there are. Okay. So before I said all the distances are, say, between 1 and polynomial n. Okay. So that means you would need, at least up to a constant, this many levels, right? Log base of 1 plus epsilon of n. Okay. What is the log base of 1 plus epsilon? I mean, that's kind of weird, right? It's hard to think about. So for small epsilon, this is actually a fine approximation. It's actually less than or equal to. This is at most log n over epsilon. Okay, so just something to keep in mind. If you want to do powers of 1 plus epsilon instead of powers of 2, You're going to give up an epsilon in the denominator, but that's it. Okay. All right, still roughly log n. Okay, good. All right, so that's why we're going to do this. Now, the data structure we'll develop is going to be scale invariant, so it's easier to just assume that the R we're working with is 1. Okay, so I just want to know some things within distance 1 or distance sigma. All right, so, well. Okay, so here's the hash function we're going to look at. Again, we're going to use Gaussians. Okay, it's going to be a randomized line embedding. Okay, so I'm going to first sample one Gaussian from the high dimensional space uniformly at random. Okay, so this is going to, this black thing is supposed to represent the origin. So maybe here's like a line. So the Gaussian is going to carve out some kind of line. Okay, and okay, so you're going to project. So the vector itself, let's say I've normalized to be a unit vector. Maybe this that's like length 1 or something, but okay. You're going to project these points onto the line. Okay, so this will kind of go here, that will go here, like this. Okay, so now I'm kind of looking at a one-dimensional space. And then now we're going to add buckets of width 1, so to speak, but I want to randomly translate it so that we don't kind of deterministically screw up people. So we pick some factor alpha between 0 and 1 uniformly at random. And so that'll maybe say this will be 0.5 or something. And otherwise I have buckets of width 1. Okay, so these dashed lines would be translated based on alpha. Okay, and so in that sense, I've created some buckets. We basically picked a random line, embedded on the line, and then bucketed it. Okay, and tried to randomize a lot of things. Okay, so here's a prettier version, I guess, of the picture prepared ahead of time. Okay. Does that function make sense? Okay. All right. So this one is going to have a few more calculations compared to last time, but hopefully that'll be okay. Right? Okay, so I guess we're going to take it. Yeah, I mean, ultimately we want to try to figure out what are the odds of x and y colliding or not, as a function of their Euclidean distance. As a baby step, this first lemma is only analyzing the effect of alpha. Okay, so let's take 2 points in our input, and what's the probability that they collide given that Gaussian vector g? Okay, so we fix g, and it's going to be something related to x minus y per times g. So, all right, so so what's going on here? So we're looking at g is fixed. Okay, so once g is fixed, xg and xy are fixed. Okay, and we're kind of looking at random buckets. Okay, and these buckets will get translated based on what's that choice of alpha, right? Okay, so so first of all, if x and if the embedded points, oh, the xy is the issue, right? Okay, yeah. I think the fancy word is active learning. All right. Okay, so The interesting case is when the distance on the embedding is less than 1. Otherwise, they'll never be in the same bucket anyway because the buckets have width 1. Everything's been normalized. Okay, so fine. Okay, so at some level we can pick 0 to be anywhere because it's sort of symmetric. So maybe for convenience I can think of 0 being here and maybe 1 being here. Okay, and depending on where alpha is going to decide where the buckets go. Okay, so maybe I'll call this alpha, and I've made this hard on myself. I think I did it. Okay, so depending on where alpha goes, this will slide. Okay, so alpha is a random value between 0 and 1. What are the odds that alpha is set? I guess it doesn't quite match like I would have liked. What are the odds that alpha is set so that x and y get split up? Yeah, so if alpha is between, then it'll get split up. If alpha is anywhere up over here, especially if I drew it correctly, then they won't get split up. Okay, so I guess that's what we have here. So whatever, x minus y g, okay, is of course fancy for xg minus yg. Okay, so that's really just the distance between them on the line. Okay, no big deal. Okay, but it makes some sense. Okay, you're now at this point we're sort of hoping that, yeah, we can talk a little bit about intuition then. We can go back to this picture. Okay, so we can see what the bucketing does. Once the embedding is set, the bucketing is going to more likely put together points that are closer together on the line, and more likely to separate them the further they are in the line. That's what the lemma said. It's not really that exciting. Okay, now what we're saying is, or what we want to know then is, if I have 2 points that are close, what are 2 points that are close? I don't know. I didn't draw them close. Okay. I have 2 points that are close. What are the odds that the random Gaussian is going to embed them closer together? Okay. But we know at least intuitively from last class, the random Gaussian will preserve length and stuff like that, right? So you are hoping that gx minus y we know that we actually know from last time that this thing squared actually does look like x minus y squared, maybe up to some constant that's fixed or something, right? So in general, we've built some intuition that Gaussians do preserve distances. Projections onto Gaussians preserve distances. The difference is that for the sake of efficiency, we only projected onto one Gaussian. Whereas last time we projected onto like logarithmically many Gaussians. And then taking the average, they're definitely going to preserve the length with very high probability. Here we're only doing one because I just want to do this bucketing and roughly keep the hashing infrastructure, which is much more efficient for this purpose. Okay, so we're not going to get as strong a bound, and we'll have to figure out how to amplify some things afterwards. But again, the idea behind doing one line is that, you get the hash function out of it. Okay. All right, so that's the intuition. Now, what do the calculations come out to? Now, I should warn you that you'll see the calculations are incredibly unsatisfying for this problem. I'll explain what I mean. It's actually quite, in a way, it's sort of, I think, creative because in some sense, it's going to take something messy and make something constructive out of it. But let's see what I mean. Okay, so now what are the odds that the h of x is equal to h of y? Okay, so this is really what we're interested in. And we did a little baby analysis before. We just analyzed the alpha part. So that'll come into play here. All right, so the probability that h of x is equal to h of y. Okay. All right. So, okay. All right, so how do I break this down? Any ideas for a first step? I have the cheat sheet written here, but I thought I'd ask. Yeah. Sorry, say that again? Is it that it's perpendicular? No, it doesn't have to be. Or I mean, I think it's sort of indifferent to that. Okay, let's here. This is going to be a little bit more calculus. What we're going to do is we're going to uh, condition on t. Sorry. What I want to do is I want to condition on this quantity, which we just analyzed. Okay. So uh, let me first just set it up a little bit. Given that this absolute distance on the line is equal to t times the probability that the absolute distance on the line is equal to t, dt. Okay, so this is just conditional expectations done continuously. So going over all t's, what are the odds of being that value of t times hashing conditional on t? Of course, this is not really well defined, so we'll replace that now. Okay, so again, it's a continuous distribution, so really the odds of being exactly equal to t is 0, so that's nonsense. But instead we want to plug in some kind of density function, right? All right, so what is this distributed as? So x and y are fixed and g is a random Gaussian. What is x minus yg? You guys remember? That's true. That's true. That is true. But this is going to be distributed as something nice with a nice name and nice parameters. You could probably guess it because there's like very limited guesses. This is going to be distributed as a Gaussian, right? Because this is really a sum of Gaussian random variables. So this is going to be distributed as a Gaussian with variance. Okay. So we had actually applied this to every row of the projection matrix last class. Every row output a Gaussian. Okay. And so I'm going to let f of t be the density function for the normal distribution from last class. It doesn't actually matter exactly what it is. Okay. But in particular, if I want to look at the odds, or the density, so to speak, so I'll put quotations around this. The probability that x g is equal to some value t. Okay, that's sort of the odds of x minus yg being equal to negative t or t. Okay, so the only difference between a standard Gaussian with variance 1 and a standard Gaussian with, a Gaussian with variance x minus y squared is you kind of effectively plug x minus y into the density function. Okay, so let me plug this in. Oh, let me plug in two things. Okay, so what we just addressed was this, and for this we have something that we just did, right? So we would get 1 minus t times f of t x minus y. There's a factor of 2 I'm missing, dt. Okay, not too big a deal, and that's really the only lemma. It's actually not even making that bold a statement. We just wanted to get to this expression. Okay, you see some dependence on the distance is maybe the main thing. All right, so yeah, the funny thing is that we can't actually, or we're not going to try to simplify this or clean it up more than that. We're actually just going to kind of treat it as a parameter. Okay, so I think we can all agree that this expression we came up with seems messy, especially if I had not hidden everything inside the f. If I had actually written out the normal density function with the e to the whatever, it'd be a nightmare, right? So, okay, but we're not going to. We're going to be kind of lazy. I'm going to let p be the value when the distance is 1. And I'm going to let q denote the value when the distance is at least sigma. Okay, where sigma was what determines a no longer neighbor, and 1 was our definition of near neighbor. Okay, so in particular, p will be an upper bound on the odds of two things colliding when the distance is. It's a lower bound on the odds of two things colliding when the distance is very small, and q is always an upper bound on the things colliding when the distance is very far. Okay, and what we're going to do is we're just going to do an analysis in terms of p and q. Okay, and at the end, understand their implications. Okay, so there are maybe some calculations related to sigma in there, but we're not going to worry about it. Okay. All right, so we'll do something similar, or try out something similar to before. We'll do our analysis in terms of p and q. Okay. So again, we're just going to group the input points by the hash code, which is just a random line embedding, and then we'll scan this same bucket. Okay. So if I do that, what's the probability of this succeeding? If there is a near neighbor, what are the odds we find it? P. Okay. And what's the expected time? Let's just treat the hashing part as, let's say it takes d time to compute the hash because you have d coordinates. By which I mean expected time to do a query. So you've already built out the buckets. Right? You first compute the hash, that's d. Okay. That should be a plus, not a t. Yeah, we might expect to have to go through qn useless coordinates, points or useless points that are far away but still show up as probability q. So something like d plus qn. If I wanted to get this to constant probability, then how many times should I repeat it? Okay. Yes. Okay. Mm, okay. If I wanted to, well, first of all, say you didn't know that. Let's say, okay, well, let's say you wanted higher probability, right? And maybe you wanted to, if you repeated this thing log n over p times, say, okay, then you'd be looking at a running time of something like d log n over p plus q over p n times log n. Log's not so important. Well, or what I really wanted to do though was draw emphasis to this q over p ratio. Okay, so p is maybe larger than q, but yeah, okay. All right, so overall this is unsatisfactory because q may be very not small enough, and okay. So what might I do to improve this? I want to try to put this on steroids. The real issue, the real bottleneck is not really p. Actually, p, is, as noted, is actually kind of high. But the real issue is that qn is going to kill you. So I want to reduce q, but hopefully we won't reduce p by too much. We'll have to see how it works out. But how might I, in particular, try to reduce q? Well, sigma's fixed, so that's an input parameter. So we already are going for a 2 approximate nearest neighbor, and we're not allowed to be like, well, here's a 10 nearest neighbor.
Are we allowed to drop, make it bigger, like make p lower?
Yeah, yeah. What I have in mind is also going to hurt p.
My thing is like, what if we say run this, for example, twice, and only consider a point if it shows up in a collision in both runs?
Yeah, so we can do something like we did for angles, which is we can have many hash codes. Okay, so let's do k of these for some parameter k to be determined, and that's just going to ramp everything up by a factor of k. So when you have points that are near neighbors, the odds of them colliding are now at least p over k. That's bad. On the other hand, uh, if the probability of if they're far away, this is going down to q over k rate as well. Okay. All right. So okay. So all right. So now here's sort of our setup, right? If I do this, what becomes my probability of success? Before it was 1 over p, now it is. And my expected time to do a query might be just for one of, sorry, that's p to the k, I'm sorry. Yes. Okay. Now to do a query, what would be my expected running time? Okay, so the previous running time times k would be this. We do actually get a better dependence on k on that second term. So we do have to compute that hash k times. That's not really a big deal. But this q to the k, is fantastic because number of points I scan is now going down exponentially. Okay. Now, to get a constant probability of success, I would repeat 1 over p to the k times. So in other words, I would take this data structure we just designed and make 1 over p to the k copies. Okay. And if I did that, then the running time looks like kd over p to the k plus q over p to the k times n. Okay. All right. So one thing nice to point out here. So this went down, that was bad, right? And so to compensate, I'm repeating the thing in proportion, 1 over p to the k times. Okay. The overall running time comes out to q over p to the k. Okay. Now, q is slightly smaller than p. Okay. The exact relation we'll figure out later. So it's not as dramatic as q to the k because that was q over p, but this is still an improvement. Okay. So q over p to the k is still better than qn. All right. So okay. All right. So now all that's left is choosing a nice choice of k and see if we can get some kind of win. The hard part is just to do anything in sublinear time. Okay, so what are we going to choose it to be? All right. Oh, no, you want to guess? Go ahead. Yes, it's going to be, we're going to do log n over log 1 of q, which will be kind of convenient for some calculations. Okay, so let's take this term. If I choose this value of k, then what does this equal? I think you'll get 1 over n times n. Okay, and then, so you get 1. Okay, so 1 is less than k, so roughly that term doesn't matter anymore. So then what about the other term? We have what appears to be 1 over p to the k times k. Okay. And if I just plug this in and I don't do anything too clever, so the outside, this is the outer k. This is not a big deal. Okay. Times, okay, so now what is 1 over p to the k equal to? What is this, right? Oh, okay, this is going to be okay. Okay, so what we want to do is write e to the log 1 over p, and then also plug in the new value for k. Log n log divided by log 1 over q, something like this. What I'm going to do is I'm going to bring that n down. Okay. We get log 1 over p over log 1 over q. This is the most important term. Okay, because I'm really interested in what polynomial dependence I'm getting on n. So here's it. Let me give it to you slightly cleaner. Very slightly cleaner. Okay. So we get, this is not so important, we get some n to the row of sigma. It's just a function of sigma. And ultimately it's log of 1 over p divided by log of 1 over q. Okay, this is going to be less than 1 So this is sublinear, but the question is kind of how much. Okay. So let me just present the theorem in full detail so I don't screw something up. Okay. So it's a bit messy. Okay. But the exact bounds, so to speak, that we get is that in roughly n to the row of sigma time, we can return the nearest neighbor, where rho of sigma is log of 1 over p divided by log of 1 over q. Okay. Where p is that thing, and then q is also this thing. Okay. So, first of all, what do people do in practice? So if you actually had a value of sigma and you wanted to figure out what this magical ratio log of 1 over p divided by log of 1 over q would be, what would you do? Yeah, you just plug it in a computer and you plot it and see what it is. Okay, and you'll see that it's less than 1, and there's some curve. Okay. Now, you can do some calculations in the back of the notes. If sigma is not too big, say sigma is, I guess, less than 1.2649 is what I calculated. Then you can show that this rho is at most 1 over sigma squared. Okay, so if sigma, again, is bigger than 1, then rho is going to be 1 over sigma squared. Okay. So, for example, if you're looking at, if you want to phrase sigma as 1 plus epsilon, where epsilon is small, and I guess it has to be smaller than 0.2649, then the bound you're going to get is something like 1 minus 2 epsilon plus epsilon squared. Here I'm just being very lazy and pointing out, okay, this thing is very similar to 1 plus epsilon squared. So there should probably be some constant there, like a factor of 2 or something. But again, it's smaller order bit. Okay. But what's really surprising about this is that for some fixed value epsilon's like 0.1 or something. All right. This is smaller than n. Okay, it's maybe n to the 0.9 or something, but it's smaller than n, so you're not actually having to scan the whole data set, and getting n to the 0.9 or 0.8 is in fact a big win. In practice, this data structure works even better actually, and you don't actually have to make as many hash codes as we're requiring here to get this kind of performance in practice. So everybody, I mean, this is very commonly used in practice. Okay. But theoretically, a key point is that we get something that is sublinear in n, and so that is really our win. Somehow we can approximate nearest neighbors in something that's sublinear or in the input size, and by a full polynomial. Okay. All right, so that's locality-sensitive hashing. This is a different example of hashing where the goal is actually to try to preserve some of the geometry and try to get points that are closer together in various different ways to collide. Thank you.